Marhaba. Okay, finally we reached the point where we will write a proof. Remember, we are learning logic and we want to use logic to write proofs. Logic has two parts: the precise language, in which we learned how to write down sentences in propositional logic and in predicate logic. And in the previous video we learned what are rules of inference. Let me do a quick recap. But again, we have a language, we have rules of inference like deduction rules, and we use the language together with the rules to construct proofs. And today we want to write proofs using the language of logic and using the rules of inference. So remember, an argument in propositional logic is simply a sequence of propositions, compound propositions. So you imagine each alpha 1, alpha 2, each one of these are compound propositions. We call all of them except the last one premises or hypothesis, and then the last one we call it the conclusion of the argument. So simply this is an argument. It's a list, it's a sequence of propositions. Now this argument, given an argument, we call it valid. We call an argument valid if it has the following property: if in every case where all of the premises are all true, then the conclusion follows to be true. So this argument, we call it valid if, suppose alpha 1, alpha 2, alpha 3 up to alpha 1 are all true, then it follows the conclusion to be true. If this holds always, that whenever the premises are true, the conclusion is also true, then we call the argument valid. Okay, so when an argument is invalid, when it's not valid, if you manage to find one scenario, one case, where all of the premises are true, alpha 1, alpha 2, up to alpha n are true, however, beta, the conclusion is false. If you manage to find such a scenario, then the argument is not valid. Okay, and sometimes instead of writing an argument in this way, we can write it in a vertical form. So alpha 1, alpha 2 up to alpha n, these are the premises, and the last one we say therefore the conclusion follows beta. Okay, so this is another way to write an argument. Now, and we said short valid arguments, like by short we mean like they contain one or two premises. Then any short valid, not any, like some short valid arguments are called rules of inference. And we introduced the rules of inference before. Let me quickly remind you with the rules of inference. The rules of inference we are using in this course. So the first famous one is a famous one called modus ponens, and it says if P implies Q is true and P is true, then it follows that Q must be true. Okay, then we have modus tollens. If P implies Q is true and the negation of the conclusion is true, then the negation of the hypothesis not P is true. This is modus tollens. We have hypothetical syllogism. It says that if P implies Q is true and Q implies R is true, then the hypothesis of the first implication implies the conclusion of the second implication. P implies R is true. Okay, disjunctive syllogism, it says that if P or Q is true, so if this statement is true and not P is true, this means that Q must be true. Okay, addition rule, if P is true, then P or Q is true as well. So notice that all of these are valid arguments. Okay, what do we mean by a valid argument? We mean suppose P or Q is true and not P is true, then you need to see that Q must be true. Okay. One way to show it is either you say if this is true and not P is true, this means P is false. So if P is false and the whole thing is true, then a disjunction, since the whole disjunction is true, then this second one must be true. So Q must be true. Otherwise, you can show that this is a tautology. The conjunction of the premises, so P or Q and not P, implying the conclusion of the argument, this whole thing is a tautology. construct its truth table, and you will find that all of the values are true values. It's a tautology, it's always true. Okay, simplification rule, what does it say? It says if P and Q is true, then P is true. Conjunction rule says if P is true and Q is true, then P and Q is true. So P and Q, this is one proposition. If this proposition is true and this proposition is true, then this proposition is true. Okay, resolution says if P or Q is true and not P or R is true, then it follows that either Q is true or R is true. Okay, the disjunction is true. Okay, we have two special cases of resolution, that when R is Q, then we get if P or Q is true and not P or Q is true, it follows that Q must be true. And we have another special case when R is F, bold F. Remember, bold F is a contradiction. It's a statement which is always false. When this is the case, then we get P or Q is if P or Q is true and not P is true, then it follows that Q is true. And notice that this one is disjunctive syllogism. Okay, now what we will do is we want to use these rules. Okay, maybe I should give this example before we move on. Notice that this argument is not valid because it is not the case that whenever the premises are true, so it follows that the conclusion is true. Well, here is an example. Suppose P is false and Q is true. Then P implies Q is true because the hypothesis is false, this hypothesis of the conditional statement, and Q is true. Okay, so this is true and this is true. However, P is false. Okay, so we found one case where both premises are true, but the conclusion is false. What is this case? It is the case when P takes the value of false and Q takes the value of true. Okay. Now what we will do is we want to use these rules to prove the validity of longer arguments. Okay, so let's move to the board and solve this question. Show that the following argument is valid. So notice that this is an argument. Why it is an argument? It's a list of propositions. These, all of them except the last one, are the premises, and the last one is the conclusion. Okay, so let me do the conclusion in pink. Okay, so here is all of these. We have 4 premises. So we have 4 premises, and this is the conclusion, and we are asked to show that this argument is a valid argument. How will we show this? So what does it mean? We need to show whenever the premises are true, whenever this is true and this is true and this is true and this is true, then it follows that T must be true. So this is what we need to show, but we will show this using the rules of inference. Let me show this. We start by assuming the premises. So 1, we know that the first premise, we want to show that whenever the premises are true, the conclusion follows to be true. So let's assume the premises are true. So I will assume that the first one is true. So not, just a second. Okay, so assume that not P and Q, not P and Q is true. So why it's true, we need to justify. We write here, it's true because we are assuming it to be true because it's a premise. Number 2, I am saying that R implies P is true. Maybe it's not true, but we want to just we only care about the case when all the premises are true. So suppose this is true and this is true because it's a premise as well. Okay, we have 4 premises, 3 and 4. Not R implies not S, and this is a premise. And finally, S implies T is a premise. Okay, so we now assume all of these 4 are true, and now we need to move using these premises and then move step by step using the rules of inferences until we arrive to T, showing that T must be true. So now we are assuming all of these are true. Now what can we do? Look, this is a conjunction. Using the simplification rule. So this is simplification applied to number 1. Remember, if a conjunction is true, then the first one is true. So this is not P. We can conclude that not P is true. Why? Because we are assuming not P and Q is true. And using the simplification rule, we can deduce that not P is true, which is the first one of the conjunction. Okay, now look at R. We have R implies P is true and not P is true. Then we can use modest tolerance here. Okay, modest tolerance applied to 2 and 5. What does it say? If you have an implication and you have the negation of the conclusion, then you can deduce the negation of the hypothesis. So we can say not R is true by modest tolerance. Okay, now look at this. Look at 3 and 6. This should tell you to use modest ponens. Modest ponens. This is applied to 3 and 6. Okay, what modest ponens says? It says that if a conditional statement is true and its hypothesis is true, look, this is the conditional statement I'm talking about. This is number 3. Its hypothesis is not R, and not R is true from here. So modest ponens tells us to conclude its conclusion. Its conclusion is S. So S is true. And finally, you see now we can get to T by applying modest ponens applied to number 4 and number 7. Again, this is the conditional statement. S implies T. Its hypothesis is true. We can conclude its conclusion, which is T. So here T. So we arrived at T, which is the conclusion of our original argument. Okay, this proves the validity of this argument. Okay, this argument, we proved its validity, which means we proved that whenever this is true and this is true and this is true and this is true, it must be the case that the conclusion T is true. Okay, and how did we do this? We assumed all the premises are true, and then we moved step by step. In every single step, we justify using a rule of inference. So we used simplification, modest tolerance, modest ponens, and modest ponens until we arrived to our desired conclusion T. And this argument is called a formal proof. A formal proof, and see, we used logic to write this formal proof. Every statement is written in propositional logic, so propositions, conjunction, implication, negation, and we used the rules of inference to deduce new statements from the previous ones, from the assumptions. Okay, so let us write down formally what is a formal proof. So let me write it here. A formal proof of the validity of an argument, of the validity of an argument say the argument has alpha 1, alpha 2 up to alpha n premises and conclusion beta, what is a formal proof? So here I'm defining what do I mean by a formal proof. It is as this example, simply it's a sequence of statements. So is a sequence, okay, of propositions, a sequence of statements, but by statements I mean compound propositions. A sequence of statements, say of the form, say the first statement is, we usually put here a vertical line. Okay. So say the first statement is phi 1, the second is phi 2, the third is phi 3, the ith one is phi I, and say the last one is phi m. Okay, remember, when do we stop the sequence? When we reach to our desired conclusion. So it should be that the last statement of our sequence, of our proof, is the conclusion of our argument. This should be beta. And what do you know about these? These, okay, let me write them now, where each phi I, so each statement in your sequence is one of the following, is either one, a premise. So one of the premises, which are alpha 1, alpha 2 up to alpha n. So say it could be that the first statement is alpha 1. The second statement, you can use, for example, alpha 4 here for the second statement. You can use any of your premises. So you can use, let me highlight the premises. So I'm saying that a formal proof, okay, a formal proof, it's a sequence of statements, but with some conditions. What are these statements? Either they are premises, so each alpha I here, either it's a premise, or inferred from previous statements, from previous statements, okay, by a rule of inference, okay, which, like this phi I, you can write it in the sequence if, say, you apply mod exponents to phi 2 and phi 3, to previous ones. So you can use the previous statements to apply a rule of inference and deduce the statement phi I. Like, for example, here, suppose this is phi I, we deduced not R by applying modus tollens to previous statements, to 2 and 5. We used statement 2 and statement 5 to get statement 6. Okay? Okay, so either it's a premise, and each statement in your sequence, either it's a premise or inferred from previous ones by rule of inference, or phi I, so I'm talking about phi I, where what is phi I? It's any statement in this sequence, in the proof, in the form, or it is logically equivalent to previous statement, logically equivalent to a previous statement. Okay. For example, if one of the states, say phi 3 is P implies Q, then we know that a conditional statement is logically equivalent to its contrapositive, so I can here write not Q implying not P. Okay, since this is true and this is logically equivalent to this, and what does it mean logically equivalent? It means it has the same truth value. Okay, then this is also true. So I can write phi I to be a logically equivalent proposition to a previous one. Or finally, we can write any tautology you want, because the tautology is always true. So say phi I plus 1 could be P or not P, because P or not P is always true. Okay, so notice what will happen, that we start by assuming some premises to be true, and then every single step, since we are using a rule of inference or a tautology or or, a logically equivalent one to previous ones, every single new proposition will be also true on the assumption that the premises are true. So until we get to the conclusion, which means that on the assumption the premises are true, then the conclusion is also true, which shows that the argument, this argument, is valid. Okay, so this is how you show what do we mean by a formal proof of the validity of an argument. Okay. Let me stop here.